Hey everyone, welcome back and let's write some more neat code today. So today let's solve hand of straights. So we're given a hand of cards, which is given to us as an array of integers. So each card has a particular integer associated with it. We want to rearrange the cards into groups so that each group size is a particular value that we're given as an input parameter. For example, one value we could be given is group size of 3. So every group needs to be of group size 3, but not only that, every single group needs to have consecutive cards in it. Basically, a group could be, let's say, 1, 2, 3, because all values are consecutive. It could also be 2, 3, 4, right? But something like 2, 3, 5 would not work, right? Because there's a hole in here. These are not consecutive. We're missing a 4, right? So one thing to recognize with this problem is how could we possibly break it down into groups, right? Like just looking at this, we have so many different options. Brute forcing it is going to be really complex, and there's not really any way to eliminate repeated work doing something like that. So we need to find some kind of pattern. So one thing to notice would be if we wanted all groups that 2 could possibly be a part of, we know that one group could be something like 2, 3, 4, right? Because our group size is 3, and this would be if 2 was in the first position. Now, it's also possible that 2 could be in the second position, right? So maybe we could have a group like 1, 2, 3. So 2 could be in a group where it's the middle value or it's the first value. But notice how we are always going to have some value in our input array that's the minimum value, right? 1 is the minimum value in this case, right? So in this case, we could have a group of 1, 2, 3, right? 1 could be the first value. Now, are there any other groups that 1 could be a part of? This is the only group that 1 could be a part of. This is what the group would look like. We can't possibly have a group like 1 or 0, 1, 2 because there's no value that's less than 1. We don't have a 0, right? So in a sense, we can be greedy. We're always going to look at whatever the minimum value available to us is, and we're going to start with a group like that, right? So we're going to basically make a group like this first. And we also notice that, yes, we could have multiple copies of the same card. So for example, we could have 2 cards with a value of 2. So one convenience thing that we're going to probably do is count the number of each card that we have, right? So basically the best way to do that is going to be with a hash map, right? So for each card, for example, 2, we would count, 2 has 2 copies in this input array. So that's what we're going to basically do. We're going to use a hash map to count the number of cards for each value. So like I said, we're going to be taking our input array and then converting it into a hash map, right? So 1 occurs 1 time, 2 occurs 2 times, 3 occurs 2 times, and I think you probably already know how to create a hash map like this. And so given that we have a group size of 3, what we're going to be doing, as I mentioned, is we're always going to be looking at the minimum value available to us, right? So for example, in this case, that's going to be a 1, right? We're going to see, can we make a group size of 3 starting at 1? Because we know 1 could only possibly belong to one group, and this is what the group would look like. So either we can create this group in which case then we're going to continue our algorithm, then we're going to refine the next minimum value. Or if we cannot create this group, that means we can't possibly put 1 into a group, so we're going to have to return false. So that's basically what I'm going to be going over. Oh, and by the way, another quick thing that we could determine is we basically need to guarantee that the size of our input array is divisible by 3, right? Because we need to break this up into group sizes of 3, so it would have to be divisible by 3. In this case, we have 9 elements, 9 divided by 3. That, there's no remainder with that, so, it's possible at least. So we're going to start at 1, right? And then we're going to check, okay, the next value that comes after 1 is a 2. So basically, we're going to decrement the count of 1, right? We've already used our 1 now. We're going to see, are there any 2's available to us? We can do that in O of 1 time because, yes, we have a hash map, right? We can basically check that instantly. So we do have some 2's available to us, right? So we're going to decrement the count of 2, set it to 1, and so far we have a 2. So now we're going to look for that last value of this group, right? Group size 3. So what's the next value going to be? We're looking for a 3. Do we have any available? Let's check in our hash map. Yep, we have some 3's. Decrement this count to 1. So we were able to create at least one group. So we created one group. Now let's see if we can create another. And once again, we are going to be looking at what the minimum value happens to be available to us. Now the minimum is no longer 1, right? Because we took the count and decremented it all the way to 0. So we don't have any 1's available to us. But we do have a 2 as the minimum value available to us. But my question is, how can we find these minimum values? Well, of course, we could just scan through this hash map, right, and find the minimum. And we could do that in O of n time. But can we do even better than n time? Well, we know a data structure that can efficiently find minimums is a min heap, right? So basically what we can do is add all these key values from our hash map into a min heap, right? So let's say our min heap initially looks something like this, right? So 1, 2, 3, 4, 6, 7, and 8, right? So clearly we have our minimum at the top. But we know as we decremented the count of 1 down to 0, we basically popped this from our min heap, right? So basically what we're going to be doing is, yes, we're going to be popping the minimum value from our min heap if the count is decremented down to 0. So now when we're actually going to be starting our second group, we can find the minimum value to start out in log n time. We know that each group is basically going to take group size to compute. So overall, what I'm saying, the time complexity is mainly going to be log n multiplied by n, because technically, the number of times we pop from the min heap could be, whatever the size of the entire input array happens to be. So this is basically what I'm saying the time complexity is going to be. But so yes, getting the minimum value is 2. Okay, do we have any 2's available to us? Let's take a look. Yes, we have at least 1 2, but we're decrementing the count now, so it's going to be 0 2's remaining. So since we decremented this to 0, we have to make sure we pop from the min heap, right? We're popping the minimum value 2. Okay, so now let's look for the next value. What comes after 2? Of course, 3. So do we have any 3's available to us? Yes, in the min heap, we do have a 3 available to us, but we're going to be decrementing its count down to 0 now. So once again, since 3 has no more values left, what's the minimum value in our min heap? Of course it was 3 because we just popped the 2. So now we once again have to pop from the min heap the minimum value, which is 3. And last but not least, we are going to get the next value that comes after 3. Do we have any 4's available? Yes, we do. So we're just going to repeat the exact same process because we see we're decrementing the count of 4 down to 0. So once again, we can pop from our min heap. We're popping the minimum value from our min heap of 4. So we once again created a group size of 3. So now to us. So basically, it took have to go. It's usually in min heaps, you can't just pop an arbitrary value. You can't just search for a value in log n time and then just pop any particular value. You can only pop the minimum value. So how can we get around this? How can I pop a 2 efficiently in log n time? Well, one workaround would be, instead of using a min heap, you could use a tree map. So in that case, you could search for the minimum value or any particular value in log n time and then remove it with a tree map. But that's actually not necessary in this problem. Let me show you why. Basically, the idea is if we're trying to pop a value from our min heap that's not the minimum value, we've already lost. We already cannot break this up into group sizes. And in that case, we would return false. Now, that's not super intuitive. Intuitive until you actually run through the example. Take a look what we're doing here. Remember how 1 is the minimum value available to us, right? And 1, since 1 is the minimum value, it could only belong to a group that looked like this, right? So if we're popping a value such as 2 or even 3, and these values are not the minimum values, we're basically creating a hole in our values, right? So in this case, okay, 2, it's true that 2 is available to us and 3 is also available to us, right? So we would decrement the count of 3 down to 1 so we could create one group. But when we try to create the next group now, we're going to get to a 1, right? And then we're going to look for a 2, but we're going to see that 2 has a count of 0. Basically, we were trying to pop a value that was in the middle of our group, so we can't create another group because we're missing that 2 value. So if we ever try to pop a value from our min heap that's not the minimum value, that means we have to return false because we have a value less than it that's available to us, like 1, but we don't have that 2 value, so we'll never be able to complete a group with this 1 value again, so we just have to return false then. So I think that's how we would solve the problem with a min heap. Like I said, it's not actually necessary. You could use a tree map if you wanted, and you could actually not use an extra data structure at all. You could just use, I think, a sorted input array, but I'm going to be doing it with a min heap because I like the way the code works out in that case. So as I mentioned, the first thing we do want to check is that the length of hand itself is actually divisible by the group size. group size. If it's not, then of course we won't be able to break this down, so we'll have to return false. And also we do want to create a hash map counting the occurrences of each value. Now I could just use a counter in Python, but I usually like to write it out just in case the interviewer wants that. So for every value in our hand, I'm going to just increment the count of n. So basically 1 plus whatever it was previously. And if it does not exist in our map, we're going to return a default value of 0. We're also going to be using a min heap, so we want only the distinct values that are available to us. So what we can do is take count.keys, which is going to be distinct values, convert that into a list, which is what min heaps are implemented as in Python. But we actually do have to heapify it, so we're going to do heapify. This is a linear algorithm. It just takes an input array and transforms it into a min heap. Now we're basically going to continue until our min heap is empty. So while min heap is not empty, we're going to get the minimum value. So we can get the minimum value from a min heap just at index 0. So min heap at index 0 is going to give us the minimum value. I'm actually going to name this first just so it's a little bit more descriptive. And so now we want to see if we can create a group size starting at first of size group size. So we're going to go for I in range, starting at the first value, right? And going up until, the group size. So just add group size to this. So the first thing we want to check is if this I value is even available to us. So if I is not in our hash map, then we have to return false because the value we're looking for isn't even available. If it is available, then of course we do have to decrement the count of this count. So I is going to be decremented by 1. And we do have to check if this count, so if it's now equal to 0, because remember, if it's equal to 0, that means we have to pop it from our min heap. But if we're popping a value from our min heap that's not equal to the minimum value in the min heap, which we know we can find at index 0, so if this is not the minimum value that we're trying to pop, that means we have to return false immediately, because if we pop this value, if we remove it, then the next group we're not going to be able to complete because we know that there is an I value smaller than this value, so we won't basically be able to complete the next group. So we'll just return false immediately. If that's not the case, though, we are able to pop from the min heap. We are popping the minimum value. That's easy to do with a heap. So heap q.heap pop from the min heap. And so that's the entire code, and if we're able to get out of this loop, we can return true. So if we never execute these two conditions, basically if a value is always available to us, and we're never popping a non-minimum value, and we never return false in either of these cases, we basically break the hand into group sizes, and then at the end we can return true. So there's many ways to solve this problem. You can use a sorted input array, you can use a tree map, or you can use a heap. All the time complexities of each solution is going to be n log n, and they all mainly follow similar ideas. So I hope that this was helpful. If it hey, than this value in either of these cases, we basically break the hand into group sizes, and then at the end we can return true. So there's many ways